Hello my friends, welcome back to another physics lesson. Last we left off, we learned how to sketch straight line motion for objects with constant velocities, and we established a few rules which we'll go over real quick. Our first rule was that a movement in the positive direction with respect to an origin point would be represented by a line with a positive gradient on the xt graph, or the displacement time graph. So as long as I'm heading in the positive direction in relation to the origin point, it's noted as an increase in the y-axis. So let's say, for example, I was negative 30 meters away from my origin point. So this point here is at time 0, negative 30 meters away. And this is my origin point. Then my beginning point on my xt graph, or my displacement time graph, would be negative 30 at time 0. However, if I began moving in the positive direction, then that would be shown as a positive linear line, assuming that the velocity was constant. So if I started at position A and ended up at position B, I would start over here on the displacement time graph, that would be my point A, and end up at point B at some time, let's call that t2. Similarly, if I started at the origin point and moved towards the negative direction, so let's say right is positive, and let's say I started at this position, we'll call this position A, and ended up at position B, then I would show this motion on the displacement time graph as a negative linear line. So say we started here at time 1, which will be 0, and the origin, x1, we'd start at the origin, 0 meters. On our displacement time graph, we would mark that point A as 0, 0, and if we were moving towards the negative direction, then we would show that motion as a negative linear line, like so. So let's say it moved to the negative 30 meters. Then we'd have t2 negative 30 meters. Our second rule was that a stationary object could be drawn on the displacement time graph as a flat line, because it wouldn't be moving in the positive or the negative direction, it'd just be staying on the same spot. So say I had an object here at time 1, and the object was still there at time 2. Then on the displacement time graph, it would be shown as, let's say this was 20 meters away from some origin point, so 20, it would be shown as a flat line. So t1, t2, and both of them would be at 20 meters. So this point here would be t1 20, and this point here would be t2 20. Now since velocity is the change in displacement over time, so let's write that down. Velocity is equal to the change in displacement over time. A steeper gradient on the displacement time curve would correspond to an object traveling with a greater velocity. So for example, if we were moving at 4 meters per second over a period of, let's say, 5 seconds, we would get a displacement of 20 meters in total. Whereas, if we traveled at a rate of 8 meters per second over a period of the same time, so 5 seconds, we'd be displaced by 40 meters, and our gradient would be steeper, indicating a greater velocity. So if I was to draw these on the xt graph, or the displacement time graph, let's say I had object 1, which did 4 meters per second over 5 seconds, so let's say this is time 5 seconds. So it would travel 20 meters. Whereas an object traveling at 8 meters per second over the same time period would cover 40 meters. And this would be shown as 40 meters over the same time period, which would have a steeper gradient, which corresponds to a greater velocity. Now for objects traveling at a constant velocity, a positive velocity is shown as a positive flat line on the velocity time graph. So if I have an object that's traveling at a constant velocity in the positive direction, I know that its velocity is not changing because it's obviously constant. So it's going to be a flat line, and it'll be shown in the top half of the graph rather than the negative half of the graph because it's moving in the positive direction. Similarly, an object moving in the negative direction with a constant velocity will be shown as a negative horizontal line. And since acceleration is equal to the change in velocity over time, an object undergoing constant velocity will have an acceleration time curve where the acceleration it will experience will be 0. And that's because there will be no change in velocity over that period of time. However, the purpose of this lesson is to look at objects that undergo constant acceleration motion and to see how constant acceleration affects the shapes of our graphs of motion. So let's look at an actual example. Let's say we have a car. Let's say we have a car that accelerates from 0 to 50 meters per second towards the east in 10 seconds. Then it maintains that velocity for 10 seconds, then slows down to a stop in 5 seconds. After that, let's say that the car remains stationary for 5 seconds and swings around and accelerates constantly in the opposite direction to a velocity of 30 meters per second west, before coming to a complete stop in 5 seconds. How would we draw out the velocity time graph and the acceleration time graph for this scenario? Now, just like last lesson, let's set a direction and break the motion up into different stages. We see that the sports car is initially going east, so that will be our positive direction. So I'll go ahead and write that down. East is equal to positive. And our first stage is going to consist of an increase in velocity from 0 to 50 meters per second. So I'll mark that down as stage number 1. We know that acceleration is equal to a change in velocity over a time period. So our acceleration for stage number 1, which I'll mark down as A1, is equal to the final velocity minus the initial velocity of stage 1 divided by the time for stage 1, which is going to be equal to 50 minus 0 divided by 10. And the 50 will be positive because it will be moving towards the east, so we will get an acceleration of 5 meters per second squared, because this will be meters per second divided by seconds. So if I were to write down the velocity values for the first 10 seconds of the car's motion, I would get t1 second is equal to 5 meters per second, t2 seconds is equal to 10 meters per second, t3 seconds is equal to 15 meters per second. And you could see a pattern emerge because the velocity is increasing by 5 meters per second all the way till t10 seconds, which would be 50 meters per second. So our velocity time graph would look a little something like this for our first stage. Five at 1, 10 at 2, 15 at 3, and so on, till I would hit 10 seconds. And this point here would be 10, 50 meters per second. Now, since the acceleration itself is not changing and it's staying constant at 5 meters per second, we'd represent this with a horizontal line. And since it's in the positive direction, it would be shown on the positive y-axis of the acceleration time graph. So we'd get a t, this would be marked as 5 meters per second squared, and it would be constant for 10 seconds. And I might just extend these graphs out because we've got quite a bit of the motion left to draw out. So let's extend this all the way out to somewhere here. And let's do the same for the acceleration time graph. Imagine that that's a straight line. Seconds, and that will be marked in seconds as well. Now let's go back up and look at the second stage of motion that this car experiences. So, after the 10 seconds have passed and the car has achieved 50 meters per second, it then maintains a velocity, the same velocity, for 10 seconds. So let's go ahead and highlight that. 10 seconds. And we'll call this stage 2. So if this is stage 1, let's go ahead and move on to stage 2. So during stage 2, we maintain this 50 meters per second for 10 seconds. So we know that that's going to be a constant velocity scenario. So our velocity is going to remain the same, and we're going to just show it as a positive, as a flat line in the positive y-axis. So that'll be our second stage. And because there's no acceleration occurring, our acceleration will drop to 0. And that will be at the same time. So that'll take us up to 20 seconds. So 20, 10, and 20. Now let's go ahead and look at the third stage. During the third stage, we see that the car slows down to a stop in 5 seconds. And let's go ahead and say that occurs at a constant rate as well. So it decelerates at a constant rate and it stops in 5 seconds. So if we apply the same logic that we did to the first stage of motion, we can say the velocity, or the change in velocity during the third stage, over time is equal to the acceleration during the third stage. And let's make ourselves a little bit of room, so let's go up here. So the change in velocity is v final third stage minus v initial third stage divided by time over the third stage is equal to a3. Now our final velocity is 0, our initial velocity is 50, and the time taken is 5 seconds. So our acceleration is negative 10 meters per second squared. So each second over those 5 seconds, the velocity will decrease by 10 meters per second. So if I go ahead and sketch that on my velocity time graph, I know my time will be 25 seconds, and I know my velocity will decrease to 0. So if I plot it over these 5 seconds, I know from 50 over 1 second, it'll go to something like 40. Then, 40 should be somewhere around here actually. Then it'll go to 30. Then it'll go to 20, then it'll go to 10, and then eventually 0. So this will be a negative linear line, and since the acceleration or deceleration is constant in this case, we will have a negative horizontal line, so which will have a magnitude of 10 meters per second squared. And that'll occur all the way up to 25 seconds. So here. Now during our fourth stage, let's see what happens. So let's go back up to our question. We see that the car remains stationary for 5 seconds. So let's mark that out as our fourth stage. So remain stationary for 5 seconds. That's number 4. Forgot to mark this as number 3. And since there's no change in velocity, and therefore there's no change in acceleration either, both of these curves will have a 0 value for their velocity and acceleration. So all the way up to 30 seconds, we'll have 0 values. So 0 value here, mark that as stage 4 just so we can see it, and a 0 value here. Now let's go ahead and look at the 5th stage of the movement. So going back to our question, we see that the car then swings around and accelerates constantly in the opposite direction to a velocity of 30 meters per second to the west. And it does that in 10 seconds. So let's go ahead and mark down the important points. So we got opposite direction to a velocity of 30 meters per second to the west over 10 seconds. And this will be our 5th stage, rather, of motion. So let's go ahead and go back to our graphs. And let's give ourselves some calculation space on the side. So let me get rid of this. So going back to our equation, we know the change in velocity over time is equal to acceleration. So our acceleration over stage 5 is equal to the final velocity of stage 5 minus the initial velocity of stage 5 divided by the time taken for stage 5. So we know the final velocity is going to be negative 30. We know our initial velocity is going to be 0 because it's starting from a stationary point. And we know the time taken is going to be 10 seconds. So we get an acceleration of negative 3 meters per second squared, which is the same as saying 3 meters per second squared, but west. So the negative just represents the direction. So on our velocity time graph, we'll have our car go from 0 to negative 30 over a period of 10 seconds. So that'll be our final point. So we'll have 40, and we'll have negative 30, which let's say it's somewhere here. And that'll be our stage 5 of movement. So we'll have 40, negative 30 meters per second. And because the acceleration is constant, our gradient will be a linear one. Similarly, on our acceleration time graph, we're going to have a negative gradient, negative horizontal line rather, and it will be of the magnitude of 3. So we'll have a negative horizontal line up to 40 seconds, and this will be stage 5. Now, in the final stage of this car's movement, let's see what happens. We see that the car comes to a complete stop in 5 seconds. And this here is our final bit, so stage number 6. So we go from a velocity of negative 30 to a velocity of 0. So let's go ahead and put that in our acceleration equation. So we'll say acceleration over the 6th stage is equal to change in velocity over the 6th stage over time over the period over the 6th stage. So we have the final velocity, which is 0, minus our initial velocity, which is negative 30, and that negative is there to account for direction, divided by 5 seconds. And this gives us 6 meters per second squared. And you might think to yourself, but the car's moving in the left direction. How come we're getting a positive acceleration? Well, that's because the acceleration is actually towards the right, which is acting to decrease the velocity in the left direction, which is what the car is moving with initially during the sixth stage. So let me go ahead and write 6 meters per second squared, and let's say east, just to clarify. So on the velocity time curve, or velocity time graph, we'd be accelerating towards the east, therefore decreasing the west velocity by 6 meters per second. So our final point on this graph, on the velocity time graph, would be 45 and 0. And because obviously this is constant acceleration, this is going to be a linear line. So that'll be our stage 6. And for our acceleration time curve, we would have a plus 6 meters per second squared acceleration before coming to a complete stop. So this is 45, and that's the sixth stage. And I think that's where I'll leave the lesson for this time. Next lesson we'll pick up exactly where we left off, and we'll go ahead and draw the displacement time graph for a situation where we have constant acceleration. Bye for now, and I'll catch you at the next one.